Hey guys, welcome to day 12 of Calculus. We're going to continue our discussion of limits and how to apply those specifically to functions. And today we're going to go a little bit past limits and talk about not just limits in the analytical approach that we've been focusing upon, I guess would be the numerical approach. And we're going to talk about how to do them graphically as well. Next time I hope into getting to the analytical part where we actually do them using the equation itself, which is a little bit of a test of your algebra skills and how well you know algebra. And so if you are really good at algebra, and if you have a really strong foundation from Algebra 1, Algebra 2, and hopefully college algebra as well, then next time should be really nice. If not, next time will feel like a slog fest where you are butting heads against a problem for a while. But I will show you the process and how it works and do as many examples as I physically have time for, so we can make sure to get every single possible thing we can to you guys as quickly as we can. Before I go any farther today, I will be reviewing from last time the process of how to take a limit using the numerical approach. So being able to do it by plugging in numbers. After that is done, we'll talk about the graphing portion, because the graphing portion is very common sense and you can get it very quickly, but it does need to be done. So let's take a look now at our first problem on the day. Our first problem today is going to look like, let's see if we can get our writing correct today, the limit as x approaches 0 of the function x over square root of x plus 1 minus 1. So this is my equation. I can note a couple things about this. First, in my equation, I note which variable I'm doing this with respect to. It's x as the standard. And secondly, I'm approaching the value of 0. Now, I showed you guys a little technique on how to do this last time. Let's refresh ourselves a little bit. What I do is I make a big little table here. In the center of that table is going to go the value that I'm approaching. I need to approach it from the left-hand side and from the right-hand side to figure out what the limit is supposed to be. And here's the thing, if I actually try to plug this thing in, if I try to plug in 0, I get a 0 on top. On bottom I get 0 plus 1, which is 1. Square rooted is 1, minus 1. I end up with a 0 on bottom. I cannot ever divide by 0, which means this is an issue. And that's why we're doing a limit. So to do this, we talked about how we could use a very, very specific function. We subtract 0.1 from our number. We call that number a or n or whatever. We subtract 0.1, 0.01, and 0.001. And on the other side, we would do the same process, but with addition. 0.001, 0.01, and 0.1. In this case, it makes this really neat little pattern. So this will become negative 0.1, negative 0.01, and negative 0.001. That's a terrible point. I'm sorry. On the right hand side, we would get positive each of those values. This is really common around 0. Okay. This creates a nice little table. And now I need to take that table and I need to plug into it. So what I'm going to do is I need to plug in to this equation. I need to plug in negative 0.1. I need to plug in negative 0.01 and negative 0.001. Then I need to plug in 0.001, plug in 0.01, and plug in 0.1. This is going to take me some time. Calculators take some time. So I'm going to shortcut that step. Give me a moment. Okay, you can see my little numbers here. I'm going to turn a little sideways so you can see a little better. So at negative 0.1, I have 1.99499. So this is going to 5 decimal places. At negative 0.01, 1.99950. And then at negative 0.01, 1.9999995. On the other side, 2.000005. At 0.01, 2.00050. And at 0.1, 2.00499. You can correct all these values just by plugging in to that function each of these numbers. Now what you might notice is the left-hand side is getting closer and closer to 2. So is the right-hand side. It's This side is getting larger each time, but it's all approaching 2. This side is getting smaller, but it is also approaching 2. So what we would say is this limit has a limit of 2. So in this case, the limit is 2. It is important to note that f of 0 is undefined. If I actually plug in 0, I do not get an answer. Okay? When I actually get here, I don't get an answer. So in other words, what makes a limit unique is that it appears, if I'm looking at this in terms of the numbers, that I should get an answer of 2, but I don't. So this is referred to in mathematics as the limit exists. A limit exists if both sides approach the same value. This is how we define a limit existing, because if both sides approach the same value, we say the limit exists. The left-hand side approached 2, the right-hand side approached 2 differently, right? This one started above 2 and got smaller. This one started below 2 and got bigger, but they both are approaching 2. And so we'd say the limit exists, and it is 2. So this limit, as we approach 0, of this function is 2. This is a separate idea from what the value of the function is. So the value of this function is undefined. And we talked about how last time that when we talk about a function, because we're talking about realistic scenarios, we don't like undefined values. We really don't care about undefined values. It's not a good thing. Let's showcase what this looks like on a graph. Because if you have a graph, you can see how this thing's supposed to fit together and use that information to actually show what the limit is without needing to go through this process. This process is rather tedious, as you might imagine, and it relies upon you picking these values first and then plugging them in correctly and then analyzing the results afterwards. There's a lot of steps here. Let's showcase how to do this exact same thing with a graph this time. So there's my graph. I'm going to need to type in that function. Now, I just type in the function, I don't type in the limit. So I would do x divided by, and in this case I would do the square root of x plus 1, x plus 1, minus 1. So you can see how this thing looks, right? But take a look at the x-axis. So we're asking the question, what's happening as we're approaching 0? So in this case, we checked values to the left of 0, right? We checked, 0.1, 0.01, 0.001, 0.0001. We got closer and closer and closer to 0. And then we did the same thing on the right-hand side, which is what happens over here. For a quick note, this half is called the left-hand limit. This half is called the right-hand limit. It is called the left-hand limit because all of these numbers on a number line are left of my original number of 0. All right, on the number line, this would be to the left, this would be farther to the left, this would be farther still. So these are all to the left of 0. These are all numbers to the right of 0. Left-hand limit, right-hand limit. So another way to talk about a limit existing is if the left and right hands approach the same value. The reason why I like this metaphor is because if I look at the picture, that helps too. Because if I put my hand on the graph and start approaching 0, so I am now at negative 0.5, now I'm negative 0.3, now I'm at negative 0.2, now I'm at negative 0.1, we get closer and closer to 0, what's happening to my function? You can see my output is getting closer and closer and closer to 2. But watch what happens when I actually get to 2. I should say, when I get to 0. because you notice that I'm looking at the x values. When my x value is 0, it is an undefined function. But if I look at the picture, I would expect the answer to be 2, right? It's logical. This side is getting towards 2, this side is getting towards 2, yet when I actually get there, it's undefined. And so from the picture, we can see my left-hand side approaches 2, my right-hand side approaches 2, and that's why my answer is, the limit is 2. It makes sense. And now, let's look at a particular function whose limit does not exist. We're going to look at it first in the graphing form, because from now on, both are an option. But afterwards, we're going to then look at it and see it from a non-graphing form. So let's take a look. In this case, I'm going to use the function, the absolute value of x divided by x. So let's look at what happens when this thing approaches 0. So if you're wondering, what I'm evaluating is the limit as x approaches 0 of the absolute value of x over x. Now, just like before, I could use the exact same numbers. So negative 0.1, negative 0.01, negative 0.001, 0 in the middle, positive 0.001, 0.01, and then of course 0.1. Cheating. Now, to save you some headache, I'm going to actually plug these in. From the left-hand side, this number would be negative 1, negative 1, and negative 1. From the right-hand side, this would be positive 1, positive 1, positive 1. And this number is undefined. So notice on the left-hand side, my numbers are all negative 1s. From the right-hand side, my numbers are all positive 1s. So in other words, in this case, my left-hand limit would equal negative 1. My right-hand limit, using the abbreviation, would be positive 1. The limit exists if they approach the same value. So what happens if they approach different values? This limit doesn't exist. So we say the limit does not exist if the left hand does not equal the right hand. That's beautiful writing, Douglas. Thank you. In this case, my left hand was at negative 1. My right hand was at positive 1. The negative 1 and the positive 1 are not the same, so the limit does not exist. It's undefined. Let's look at our graph. And see if we get that exact same solution. Let me get rid of this red one here. So here in blue. From the left, as I approach 0, remember I'm approaching the x value of 0. So I have to be approaching 0 on the x-axis, which means I can start at like negative 1 and get closer and closer and closer, but I have to do it on the grid. So at negative 1, I'm at negative 1. At negative a half, I'm at negative 1. At negative 1/10th, I'm at negative 1. At negative 1/100th, I'm still at negative 1, like I'm at negative 1 the whole time, right? What happens on the other side, right? At positive 1, I'm at 1. At positive 1/10th, I'm at 1. At positive 100th, I'm at 1. But when I get to 0, it's undefined. So from the left, I should get negative 1. From the right, I should get positive 1. Yet when I get there, they don't line up. And we'd say this limit does not exist. Going back to my list here, notice that also f of 0 doesn't exist. So notice it's possible for the limit to exist, but the value not to. It's possible for the limit not to exist and the value not to. The limit is separate from the value itself. Sometimes the limit exists, sometimes the limit doesn't exist, whether or not the value exists. And that's what makes this so important. These two statements can be written one other way. So this is where we start getting a lot of terminology here. If I just wanted the left-hand side, we write the limit as x approaches 0 from the left. If I just want the right-hand side, so take a look. In this example, I did the absolute value from the left-hand side. This negative sign indicates it's from the left. This left-hand limit was -1. The right-hand limit is +1. We'll talk more about these at a later time. I'm not worried about these today. They are coming up, but I wanted you to see this before we got there, just so you could get an example. This is what I'm really worried about. Can you look at this function and be able to do the table? Can you look at this function and be able to do a graph? Let's look at another one. So, now let's look at one where it's the limit. Oh, I don't want to do limit. I want to do 1 divided by x squared. Okay, let's zoom out. Let's see what's going on here. Okay, this looks intriguing. This has real promise. Let's quickly go to the table and see what's happening here. So, I do the limit as x approaches 0. There are a lot of zeros today, but this this applies to any number of 1 over x squared. So again, I make my little table, and I do -0.0, or -0.1, -0.01, -0.001, 0, positive 0.01, 0.01, and 0.1. Okay. Once again, at 0, my value is undefined. So again, f of 0 is undefined. So there's no value when I get there. But the question is, what am I approaching? Well, if I plug in -0.1, this is actually 100. This becomes 10,000. And this becomes 1,000,000. On the right-hand side, same thing. So if you look on the left-hand side, it starts at 100, goes to 10,000, goes to 1,000,000. You'll notice that this number is getting bigger and bigger and bigger. In fact, it's getting bigger very quickly. And if it's not clear, we could go farther, right? We could test like, say, -0.0001, right? And then positive 0.0001. But what you'll find is that since it keeps getting bigger, we call this, of course, infinity. From the other side, the same thing is happening. These are both approaching positive infinity. So does that mean this limit is equal to infinity? Well, it turns out, sort of. So, in general, what we typically see is that most calculus books would say that this limit would be infinity. However, there's an important thing I want to make sure to note here in this little definition. The limit exists if both sides approach the same value. They have to approach a value. Here's what's weird. Infinity is not a number. A number can be defined with very specific properties. And one of the great debates of mathematics is whether or not infinity is a number. Infinity is not a number, right? I can't add or subtract with it. I can't multiply or divide with it without breaking a bunch of rules. I'll spend one day this week talking about this. But in general, infinity breaks a lot of rules. And so infinity is not a number, it's a concept. because it is a concept, it is not a value, meaning that in this case, this limit does not exist either. It has to go to the same value, a number, right? It cannot go to infinity or negative infinity. Yes, these are both going to infinity, and that's important. However, infinity is not a number, so therefore the limit does not exist. It cannot possibly be a number. Let's look at the graph. So, as we approach from the left-hand side, you can see that we're going to get bigger and bigger and bigger values. It's clearly going upwards, quickly going off the page, way up there. But at 0 itself, there's no answer. On the other side, it's also approaching a very large number, shooting way up there. Whoop. But again, it's not coming to a value, right? It's not going to 3. It's not going to 2 or negative 2. It's going off the page. Because it's off the page and it's going towards infinity, we would say that in this case, it simply does not exist. This limit doesn't exist. It's a minor thing, but very, very important. Your limits have to approach a value. If they don't approach a value, they don't exist. All right. Last thing I want to talk about. One second. Okay, so let's make some brief notes here. Okay, so when you're analyzing a limit, there's a couple of scenarios. One, same value. If that's the case, we say the limit, let's call this value, L for limit. We would say the limit as x approaches that number is equal to L, because it's the same value. What happens if they approach different values? Well, if they approach different values, we'd say the limit as x approaches n doesn't exist. What if they approach infinity or negative infinity? In that case, we'd say the limit doesn't exist. So these are your 3 scenarios we talked about so far. Now, when you have an equation like this one, this is pretty simple to do because you can do it, numerically by plugging in, or you can do it by looking at the graph, right? We can say, here's my graph, boom. We can analyze the limit using that graph and we're done. But you gotta be able to do both. Now, there's one other thing that can happen that is rather unique, and for this one, let's analyze this example. I'm going to put a 4 here because it's coming up, but I have to use space underneath. What if I have a function like this? The limit as x approaches 0 of sine over x. Now, this may look like a standard trig function, and so you may be asking yourself, well, what's going to happen? What makes this one so unique? Well, in this case, I want to look at the graph. Oh my, what is going on in here? Well, it turns out what's happening here, and this is a really cool equation for this reason, this is an example of what we call oscillating behavior. Oscillating behavior is when your function doesn't ever approach a single value. It's swinging back and forth between a bunch. It's making these lines. And this is another example where the limit doesn't exist. And so you can see, like, of the 4 scenarios we talked about, 3 of them mean they don't exist. Only one of them is the perfect scenario where the limit actually exists. That's really important to understand. So let's go back to that picture. You can see that if I'm trying to approach 0, right? If I go here, like, it's continually swinging back and forth. It's going up and down, and you can see how it's oscillating. As it get closer and closer to 0, it keeps swinging up and down and up and down. And even if you zoom in, like, it gets really trippy after a while. I love doing this when I'm super poor at my life. but it swings back and forth all across here. Like, it never gets to a solidly defined value. Like, 0 is somewhere in here, but 0, you could think it's up here, you could think it's down there. Like, there was an argument in mathematics for a long time about which one it was. It turns out it doesn't exist. It just doesn't. That's why it's a big green blur here. I can keep zooming in as far as I want, and there's no answer here, because the answer is everything. And if I'm not getting a single value, right, I'm supposed to get the same value. That indicates we should get one value. If I'm getting multiple values, like in this example, then it doesn't exist. It's a neat little function, right? It's not super neat, you know, over here, but in the middle here, some cool things happen. Okay. Now, coming to different values can have a variety of different looks. Let's look at a piecewise function. So in this case, I'm going to make the piecewise function. Let me do my brackets quickly here. See, brackets. Okay. Equal to brackets. Okay. I would do, the first thing you need to do is title it what the function is. So we do x squared for x greater than 2. Let's do this wrong. Maybe let's do it the other way. There we go. There's my graph. And then do the same thing, but instead there we go. Let's look at this graph. Okay, if I asked you about, for example, in this graph, the limit as x approaches 2 of this function, f of x. Well, we can look at this picture and ask what's happening from the left and from the right. So as we approach 2, from the left, what's happening to my number? Well, from the left it's getting larger and larger and larger, but it appears to be approaching a singular value of 1. So, in other words, if I was to look at my limits, if I was to write a table for this thing, right, with 2 in the center, to the left of 2, this number is getting closer and closer and closer to 1. If I actually pick my numbers here and do like 1.9, 1.99, and 1.999, if I actually do that, they will all get closer and closer to 1. If I did it from the right-hand side and did, 2.001, 2.01, and 2.1, if I did it from the right-hand side, let's look at the graph a different way. Did it from the right-hand side, right? It starts up here, and it gets closer and closer and closer. But what value is it going towards? It's going towards a value of what looks like close to 4. And so if I look at that function, from the right-hand side, this side is approaching 4. Because these two are approaching different values, right? The left-hand side is approaching 1, the right-hand side is approaching 4, we'd say this limit does not exist. And I can either find that by plugging into the function, or I can just look at the picture. In other words, does my left-hand side and my right-hand side match? Do they go to the same number? Can I trace my paper and have them meet up in the middle? Not one up here and one down here. No, that limit wouldn't exist. Not one up here and one down here. Not going to infinity. Like, they need to meet up at the same spot. Picture, Sistine Chapel's roof. God pointing down to man and saying, limit, boom. Okay? Now, in this example, what I want to make sure to point out, because of how these pieces were drawn, the value of 2. Okay? This question, the value of 2 is 1. Why is it 1? Because if I go to my picture, I can take 2 and plug it into this bottom equation because it's less than or equal to 2, which means I have to plug it in this one. I can't plug it into that one. If I plug it into that one, I can't plug in 2 because, well, x is supposed to be greater than 2, so I can't plug into that one. If I plug in 2, which means that for this example, this one indicates a function whose limit doesn't exist, but whose value does. That's a big difference. Because we can have functions where the limit doesn't exist and the value doesn't exist. We can have functions where the limits do exist, but the value doesn't exist. And we can have functions where the value exists, but the limit doesn't. It's because they're separate ideas. That's the big thing. The value and the limit are separate ideas. One, the value asks what's happening at, a point. What's happening at x equals n. The limit is what's predicted at x equals n. Based on the graph, where am I approaching? Based upon the numbers, where am I approaching? What am I getting close to? Limit versus value. They are separate. So one can exist and the other not. They could both exist. They could both not exist. It depends. That's why you have to know them. So that'll be it. I'm sorry for going over a minute 30. You have 10 problems tonight. The first couple all deal with the graph, so this should go by really quick. But the last 2 will take some time because they ask questions about the value and they ask a different question about the limit. And so make sure to take your time on the last 2 questions, as those 2 are the ones that are the really big ones and probably will be your next quiz. So that'll be it. I'll see you guys tomorrow. Bye.